Give me some fingers. Give some fingers up if you think you know. I'm seeing no fingers. Degree 0? What's the degree of this polynomial? Any guesses? Okay, would you take a look at the highest exponent you see there? What is it? Kayla, what is it? What's the highest exponent you see? 4. So the highest term, the term with the highest exponent, is going to give us the degree of the polynomial. So this polynomial is degree 4. To know how many real roots there are, because we're going to go back to when we talked about imaginary roots, or imaginary numbers a little bit tomorrow. To know how many real roots, we're going to look at the graph. The word root is the same as the x-intercept. All right, so I don't even need you right now to find exactly what they are. We're going to just take a look at the graph and see how many times this touches the x-axis. Okay, how many times? More? 4, okay. And so if I asked, like tomorrow we're going to kind of go through a whole process of figuring out how many are real, how many are imaginary. Today we're going to say all of these 4 are real, okay? So then what is the value of my x-intercepts? Can you guys tell what, from my graph, what you think they are? Or not? I'm going to zoom in a little bit. I'm going to go from -10 just to 2 and see if you can see it a little bit better, because they're all over here. Each one is a tick mark. You see where they cross. Okay. To me, just guessing, that looks like -1, -2, -3, and -4. So the values of the x-intercepts are -4, 0, -3, 0, -1, wait, -2 I missed, 0, and 1, 0. So in this case, roots, that word roots, and x-intercept mean the same thing. We're going to talk about later how when they're imaginary you can't see them. But for today, that just means there are 4 roots. The way I would write them as roots is not as an ordered pair. So -4, -3, -2, and this should be a -1, right? Okay, kind of like from yesterday, you did a nice job on this. If I wanted to do a sketch of my graph then, just kind of looking at what we have here, I am going to have, remember, a positive leading coefficient, so up, up, and looking at the graph, this comes down, crosses, and then crosses again. Where does it cross the x-axis, by the way? Hopefully you didn't forget everything from yesterday. Where's this cross the y-axis? Sorry. 24. Yeah. So somewhere up there. Okay. So the connection is, what I want you to notice today is this degree is going to tell us how many total roots something has. Okay. What we're going to notice is they're not going to always show up on the x-axis. Today they did. So today we're going to focus on is something called the rational root theorem. What in the world does that mean? Well, I notice that it has the word rational in it, and the rational word starts with the word ratio. Isn't a ratio a comparison of things? No, don't know? Ratio is when we compare two quantities, but what I want you to think of this at is these are things that could be written as fractions. Rational numbers could be written as fractions, okay? So an example of a rational number would be 1/2. These are just examples. How about 3? Could you write 3 as a fraction? Three over 1, so 3 is a rational number. How about 2.5? Could you write 2.5 as a fraction? Isn't that the same as 5 over 2? How about 0.3 repeating? Is 0.3, could I write that as a fraction? Who knows which fraction that is? That's 0.6, good. 0.6 repeating. It's 1 over 3? Yeah, okay, so I'm trying to give you things in other forms that you might think, but they're rational. The big deal here is they are exact numbers. For instance, I'm going to give you something that's not rational. Have you guys heard of the number pi before? Okay, it goes on forever, has no pattern, not rational. Let me give you something else that's irrational. The square root of 11. Do you know the square root of 11 exactly? Do you know the square root of 9 exactly? What is it? 3, okay? That could be rational. But the square root of 11, I don't know exactly. So things like that are square roots of not perfect squares, those are not rational. I'm only telling you this because this is only describing a certain kind of zeros today. Here's how you find them, okay? The possible rational zeros is another name for root, of a polynomial the possible or rational, so notice I know it's possible, so we're going to make some lists today, are P divided by Q. I'm just going to describe what that is in a second. So that's key here. Where P are the factors of the constant. The constant is another name for the last term, and it does not have a variable. So this P is going to be a factor of the constant, or the last term. Okay, would you guys look up at my polynomial above? I'll tell you what Q is in a second. Would you put a box around the last term or the constant, please? Hopefully you put a box around 24, okay? So the things that go on the top of my possible roots are factors of 24. Somebody give me some factors of 24 that you know. 4 is a factor of 24. What's another one? 6, 4 and 6. Logan says 2 and 12. 8 and 3, 1 and 24. Okay, so when I'm saying factors, that's what I'm talking about. All right, so that's how we're going to find the things that go on top. Q. Are the factors of the leading coefficient. And we've used that terminology before, so I think you guys all know what that is. So Q, which is going to be our numbers that go on the bottom, are just going to be the factors of the leading coefficient. So sometimes people screw that up because this is the first thing you see in the polynomial, and some human nature is to want to put that on the top of the fraction, but those things are going to go on the bottom. And the factors of the constant term go on the top. Okay. Well, what in the world does this all mean? So let's take a look. I'm going to just kind of put a little box here for the rational roots. And let's take a look at this example that we did up here. Okay. And I'm going to make a list of potential rational zeros from this theorem. Okay. So how I tell students to do this is I make a P over a Q. So would you do that, please? Make a P over a Q. And then I make this little diagram, and this little diagram is going to help me make my list. So you guys already told me what the factors of 24 are, and I'm going to list them all. Be careful. You told me positive ones. We also have to include negatives. So you told me plus or minus 1 and 24, right? I'm going to do them in order. What else? Wasn't 2 a factor? So I'm going to write plus or minus 2 on my list. By the way, if you don't like to do them in order and you like to do them in pairs, that's fine. 3 and 8. So plus or minus 3. 4 and 6. I'm going to run out of room. Plus or minus 6. I'm going to go up. Plus or minus 8. Plus or minus 12. Remember my 12 and 2. And also you have to include plus or minus 24. So sorry about my L-shaped here. I ran out of room, so I'm going up the paper. Those are all the possible numerators. Here's the good news. Look at the leading coefficient. What is it? No, the leading coefficient. 1. So on the bottom, I put the factors of the leading coefficient. I had so many to put on the top, I have hardly any to put on the bottom. But you do have to write them down. The only thing that goes into 1 is plus or minus 1. In a minute, we're going to do one where there's more on the bottom. So here's what my list is. So now we write our list. And this one you might think, well, why do I have to write my list over again? And because you're dividing by 1, you really don't. But when there's another number on the bottom, then I would have to make sure I divide by those things. Here's the deal, guys. These only go on the top, so don't try putting them on the bottom. So the list of potential zeros were, I'm going to put a plus and minus in front so I don't have to write it out 15 times. Plus or minus 1, 2, 3, 4, 6, 8, 12, and 24. And so today, the very first thing we're going to do is we're going to find our potential list. That's step 1. We'll practice that in a second. Step 2, using this as your guide, then we already found them. We're going to make educated guesses to what we see on the graph. And you said, what did we see in the graph? What were the roots or the zeros? What's this one? -1. Don't you see that that's on my list? And -2 is on my list. It just helps us figure out what the potentials are so we know what to choose. Okay. So going back to the last test, how could you use synthetic division to check if something really is an x-intercept or a 0, what would you be looking for? Has to do with the remainder. Yeah. So a way that we're going to check or verify is we're going to look at the graph and we're going to make a guess, okay? And then we're going to use synthetic division to verify which ones are. Okay. We're not going to dabble here. Yep, this will be tomorrow. The fundamental theorem of algebra says this, but we're not going to write it down. The degree of the polynomial is how many roots it has. So if it's degree 4, it has 4 roots. But tomorrow, I don't want to dabble in this yet because tomorrow we're going to talk about how you might not see them all on the graph. And so we'll talk about how you find them. Okay, so what we're going to do together is I have a worksheet that you're going to do the odds on, but just so